Warahmatullahi ta'ala wabarakatuh. And good afternoon, ladies and gentlemen. We are proud to continue with the third lecture of our Faculty of Engineering flagship webinar program called Distinguished Lecture Series, brought to you live by Faculty of Engineering, Universiti Teknologi Malaysia. You are with me, Anazida Zainal, hosting the talk today. It's a great pleasure for me to introduce our prominent professor who is going to give a talk on deep learning. Current approach to creating artificial intelligence, or rather we call it AI, is radically different from previous approaches developed over several decades. It is based not on programming computers using logical rules, but on showing examples to the computer in a process known as machine learning. On the other hand, the deep learning is a subject in which we should all be deeply interested because it's about the machine that learns patterns in the images or the data that is presented with, rather than requiring the human operator to define the patterns that the machine should look for in the image or the data. So our speaker today, Professor Sargur Srihari, is from University at Buffalo, the State University of New York, United States. But currently he is in Bangalore. So we have like 2.5 hours difference in terms of time. So the topic for his presentation is learning deep learning. Prof. Hari has an impressive artificial intelligence and machine learning knowledge and experience. To further introduce the speaker, I will pass the session to Professor Muhammad Rafiq Abdul Qadir, Dean of Faculty of Engineering, Universiti Teknologi Malaysia. Over to you, Prof. Rafiq.
Thank you, Anazida. Assalamualaikum and hello. Welcome, everyone. And welcome to UTM Engineering Distinguished Lecture Series, our third lecture in the series. My name is Rafiq and I am the Dean of Engineering, Universiti Teknologi Malaysia. Today, it is my utmost pleasure to welcome Prof. Sargur Srihari to our program. Prof. Srihari is currently the Satish Dhawan Visiting Chair Professor at the Indian Institute of Science. He is also a State University New York Distinguished Professor in the Department of Computer Science and Engineering at the University at Buffalo, State University of New York. A research laboratory that Srihari founded at Buffalo, CEDAR, developed the world's first automated system for reading handwritten postal addresses. It was deployed by the United States Postal Service, which saved hundreds of millions of dollars in labor costs, helping keep US postal rates lower. A side effect of this project was that it led to the task of recognizing handwritten digits to be considered the fruit fly of AI methods, the starting point for every new machine learning algorithm. Prof. Srihari spent a decade developing AI and machine learning methods for forensics, focusing on pattern evidence such as latent prints, handwriting, and footwear impressions. In particular, quantifying the value of handwriting evidence to allow presenting such testimony in US courts. Prof. Srihari has served on the National Academy of Sciences Committee on identifying the needs of the forensic science community, which led to an influential report. He has also served on NIJ, NIST, committees on human factors in fingerprint analysis and handwriting comparison. Prof. Srihari currently teaches 3 courses: Introduction to Machine Learning, Deep Learning, and Probabilistic Graphical Models. His publicly available course slides are widely used and included in a list of top 10 top-notch free courses in machine learning. Prof. Srihari's honors include Fellow of the Institute of Electronics and Telecommunications Engineers, IETE India, Fellow of the IEEE, Fellow of the International Association for Pattern Recognition, and Distinguished Alumnus of the Ohio State University College of Engineering. He received an Excellence in Graduate Mentorship Award from the University at Buffalo in 2018. Without further ado, I call upon Prof. Sargur Srihari for his lecture. Over to you, Prof.
Yes, good afternoon, good evening, I suppose, in Malaysia, good morning in the UK, and it's afternoon here in India. So thank you very much, Anazida Zainal, for taking the initiative to invite me back to Malaysia, at least virtually. I had a wonderful time visiting there some time ago. And Professor Rafiq for going through and setting up this whole program through UTM. So today I will go over a topic which I've called as learning deep learning. Of course, the first word learning is about human beings learning it, and deep learning is about machines that learn how to do things. So we want to learn how machines learn. So that's what learning deep learning is about. And so the way I'm going to give this talk
Okay, sorry for the interruption. Seems like the connection to Bangalore, we are having problem with the connection for now. I hope the connection will come back and we are able to listen to the talk from Prof. Srihari. So basically today, he's going to talk about deep learning and the components of deep learning. Because deep learning is actually another branch of machine learning. It's quite new and many people find it interesting because deep learning require less intervention from human. For example, in normal machine learning, human has to define what are the features of the data that we need to learn. But in deep learning, on the other way, the method of learning is the deep learning itself is going to find the features, the interesting feature or the feature that is significant to define the data. So I find it very interesting. We hope we can hear from him soon because this is a very good topic. Prof. Srihari has quite an impressive publication. If you Google, you can find that most of the lectures he put on internet as well. Quite a generous person, and also the paper mostly on machine learning and artificial intelligence, mostly on the handwritten digit recognition. For example, you may find or you may know the writer based on the handwriting. By recognizing the handwriting itself, you know who is the person. Okay, but as said by Prof. Rafiq previously, his work was commercialized and was, I think, implemented at US Postal, whereby they, instead of people who is filtering the letters, okay, this particular machine, or rather the engine that he developed, is used to recognize the addresses on the letters itself. Okay, seems like our team is trying to continue to try to get the connection back. Okay, okay. Okay, basically just to fill up the time because we are still working on getting the connection back. I got to know Prof. Srihari based on his publication, and last year I got an opportunity to meet him personally during one of the summer school somewhere back in July last year in Poland. Yeah.
Okay, I'm back. I'm back. Thank you for going on, Professor Anazida. I hope you can hear me now. Okay, so I was just saying that my talk is going to be about learning, deep learning. And so here are the topics that I plan to cover. First of all, artificial intelligence and the approaches to artificial intelligence, in particular the deep learning approaches,
Seems like the connection is again disconnected. Um, he is in Bangalore. Maybe that's the reason why. Okay. Okay, never mind. Let me continue with how I met Prof. Srihari. Okay, so last year I got a chance to attend a summer training camp in Warsaw, Poland, where he gave a lecture on explainable AI. So basically, the challenge in explainable AI is to explain what is actually the learning done by the machine. For example, sometimes people call AI like a black box because we don't know what is actually happening inside the box. Okay, because they learn on their own. So there is an area which he also has passion in, which is explainable AI. So now there is an attempt to understand how the learning is done by this particular machine learning or the black box learning. Okay, so that was the time when we met him, and after that we started to collaborate on a few other things. Okay, I hope we can get back the connection. Okay, all right. And if you have time, you can Google about Prof. Srihari. Especially those who are teaching artificial intelligence or machine learning, introduction to artificial intelligence, he has shared a lot of class materials, lecture materials on his website. Okay, so perhaps we can take it and use it as a guidance or help our existing materials, teaching materials to give to the students. Okay, our team is still working on it. I got a message that we are trying to connect to Prof. Srihari. Okay, they are still working on it. Okay, okay. Um, in fact, I've read some of his papers on the digit recognition. Basically, on the digit recognition that he was working with at that time was to recognize the digit itself, because people have different styles of writing. Sometimes people write slanted to the left, slanted to the right. Some numbers are not well connected. For example, number 6 is not well connected, the lines. So the research is more on recognizing these written digits, okay, or written or handwriting. In fact, from there, they work on analyzing who is the author to that handwriting. This is especially quite beneficial in terms of forensics investigation. For example, in the previous time, okay, Prof.
Yes, I have never had this kind of flakiness. I've been doing this for 6 months. I've been spending a whole sabbatical semester here in India. I've been conducting my lectures at the Indian Institute of Science every Monday, Wednesday. I've never had this type of breakdown, but usually I don't give my lecture on Sundays. So it could be something to do with everybody being home on a holiday and they're watching videos or whatever during the coronavirus situation. Anyway, let's hope it goes, but this is how it's going to be. We're going to be on and off, but it does come come back, as you can see. So it's not like it's not going to be possible. All right, then I'll cover AI, deep learning, underpinnings of deep learning. Then I'll talk a little bit about calculus, linear algebra, probability, computational complexity, which I regard as the main preparation topics for a student wanting to work in AI and machine learning. And the point I'm going to be making is learning machine learning or learning deep learning is not like saying, okay, I'm going to pick up a book on networking for dummies or a book like that and say, I'm going to learn deep learning. It is unfortunately not quite that simple. That deep learning methods are based directly on ideas from calculus, ideas from linear algebra, ideas from probability, and even computational complexity. And without knowing something over each of these topics, you really can't learn the topic, I feel. It is not quite like, I'm just going to go use a standard library. But anyway, let's see how it goes. So I'm going to cover these types of topics today. All right. First of all, we don't need to talk much about that AI is everywhere. Until the coronavirus came out, all the news of the world used to be about AI and how it's implemented using machine learning and so on. Every newspaper article every day, every day there would be some news about this topic. But anyway, so we all are aware of AI. Whenever we do a Google search, there is AI going on. It's trying to figure out with its intelligence as to what you might be asking about. And or the search engines such as Google or Baidu. Baidu is one founded by my former student in China. And understanding speech like Siri or Alexa and so on involve artificial intelligence. Autonomous vehicles, which we hear about a lot about the research on driverless cars or trucks and so on, all of which based on AI. And yeah, please go on. Yes. So then we can ask, how are these programmed? And the first thing we can all agree upon is some kind of knowledge is needed by AI programs. And you can think about that knowledge is probably intuitive and subjective. And, about driving a car, for instance, when do you turn the steering wheel, when do you press the brake and so on, a lot of intuitive knowledge goes into it. Even recognizing handwritten digits, we have some intuitive knowledge about we don't have like a simply stored patterns. We have some knowledge about these things, and so the challenge then becomes how to get all this into a computer. So the first approaches to AI were about knowledge-based approaches, where we would hard code the knowledge, saying, okay, there is the diagram on the right-hand side shows the input goes through a hand-designed program to an output. So we refer to that hand-designed program as a knowledge-based approach, where we hard code knowledge. If you're trying to drive a car, the input coming in is the sonar and the camera input and so on, that has to translate into the steering wheel and the brake and accelerator and so on. So that's the input-output mapping, and the hand-designed program would be to tell it when to do what. That would be a knowledge-based approach to the problem. To write a code like that, the programmer or the team of programmers would have to have a deep knowledge about the problem domain. So, for instance, even for a simple task like handwritten digits, you would have to have a knowledge about how they're shaped and what are the exceptions and so on. Okay, so that is the classic approach. And the classic approach to AI is not very practical in terms of going on to new applications. There's only simple ones we know about. And we can, think about new applications. We want to do AI for something else. And this kind of approach of having a programmer having full knowledge of the domain, it's just impractical and not possible to proceed further, which is what led to the newer approaches, one based on machine learning. So in machine learning approaches, we, of course, we can divide between simple machine learning approaches and deep learning approaches. Simple machine learning approaches do the mapping from the input. There would be some feature engineering that would take place. A programmer would not completely map from input to output, but at least would take some features from the input and write the mapping function from the converted features into representations and into the output. And there again, this machine learning approach was not good enough to be transferred to new tasks, because you would need good feature engineering, writing code for extracting features, which is what led to the onset of deep learning, which says we can't even write programs that would extract features. That would take too much effort. We need to go from the raw input to the output. And deep learning involves not only doing the final classification task or regression task, but also to take the input and convert it into features which would then be mapped by a machine learning program, maybe a simple machine learning program, to do the output. Okay, moving on to the next slide. Okay, so we now have three paradigms of AI. Leftmost one is the rule-based system, which goes from input to a hard design. We have a hand design program to output. And the classic machine learning is going from input to hand designed features, so that the programmer says how I'm going to like if you have an image, the program would say, why don't we select this color pixels or this region and so on. The programmer would write that code. The mapping from the feature shown in gray would be done by a machine learning program to go to the output. We refer to that as classic machine learning. Representation learning is what today's AI is all about, where we go from input to features to mapping from features to output. The gray boxes again are machine learning programs, and the rightmost flowchart going from bottom to top is input to simple features to additional layers of more abstract features and mapping from features. So it kind of indicates what deep learning is about, that there are layers and layers, and we'd go from simple features to additional features to, and then the final step would be the classic machine learning of mapping features to output. So that's what deep learning is about, is there lots of layers of machine learning getting higher levels of abstraction. Okay, moving on. So let us now try a formal definition of deep learning. So what is deep learning? So we can say deep learning has three components to it. One is neural networks. That deep learning methods are inspired by neural networks of the brain. So we are going into some kind of models here that behave somewhat like the brain. We have neurons and connections to between neurons, and neurons would fire, and they would take inputs from other neurons to fire or not fire. So that is just one possible inspiration, but there are several others. There's many algorithms that we come across that are brain-like. So deep learning is neural network-like, inspired by neural networks of the biological brain. The second component of deep learning is that it's about learning. Of course, the word itself says, the phrase says deep learning. It is about machines that discover rich and useful representations. This is the point I made earlier on, that it is not about human beings writing code to figure out what features or what representation of the world we need. It just discovers, the machine itself discovers, going from, let's say it's about an image of animals like cats and dogs and horses and cows. We don't write code to say what is the distinction between each of these animals. It would have to learn these things, and it would learn rich and useful representations. Useful in the sense it's able to use these to map what kind of object are we looking at. Rich in the sense it has got a lot of useful information available for other tasks, and perhaps even for explanation. As we could ask the system as, why did you say it's a horse? So it should be able to look at what it has learned and say, I'm able to say it's a horse because of the legs or ear or whatever, right? So that is about the second component of deep learning, is the learning component. The third part is about the depth. So why do we use the word depth? Depth is in terms of architecture. You can say layers and layers. Each layer learns a representation. We can also think of it mathematically as it's a composition of learned features and functions. So it is a function of a function of a function. If you think of an input-output mapping as a function, the box in the middle is a function that takes an input, maps it into an output, then that's a function. But we are saying not only is it one box, but another box on top of it, in which case the second one is a function of a function, and so on. We refer to that as composition of functions. So deep learning is characterized by several layers of composition. So the levels of abstraction are extracted somewhat like human beings do. So we are able to explain things at a higher level than at the pixel level, saying, why did you say it was a dog or a cat? It's not because the million and 17th pixel has a certain value. That's not the level we talk at. We talk at more levels of abstraction. So those are the three aspects of definition of deep learning. And the notion of deep learning is aspirational, that it doesn't say how you're going to do it. Maybe to some extent the architecture, but deep learning is a goal and does not say how. If such as you have to add this kind of a prior to learn the higher level representation and so on. We allow for a variety of knowledge to be incorporated. There is some level of outside knowledge that could be incorporated. And so deep learning, we say, is aspirational, like saying artificial intelligence. What do you mean by artificial intelligence? It is aspirational in that a computer is said to perform things intelligently. If done by a human being, we'd say that is intelligent. So it is kind of saying a goal of a broad sort. Machine learning is also like that. Deep learning is also aspirational and does not say how exactly it is to be done, because there are varieties of ways of doing it. So I'm going to transition from here to what are the underpinnings of deep learning and what is it that you need to know about to be able to either be a practitioner of saying, okay, I'd like to deep learning, I'd like to use deep learning to solve some problem of the day, or I want to be a researcher in deep learning and AI. Graduate students want to be researchers. They're looking for what kind of problems, interesting problems are there. So what should I learn to become a researcher? So then we can look at the underpinnings of deep learning. I got three columns here, basically. The first column is about neurobiology. There is a photograph of a human brain, and so we need to know something about that. And the second one is about statistical physics. Interestingly, statistical physics comes into play. It's about statistical physics, what about things like gases and atoms and energy, and in statistical models we have probabilities of configurations and so on. So same ideas come into play in deep learning, interestingly. And the third column is about distributed computing. It's about computing that is not done done totally sequentially, but in parallel, lots of computation is getting done simultaneously, and that is a hallmark of deep learning. And below, I've got the famous thinkers who have made major contributions to each of these three areas. And below the brain picture, I have portraits of Warren McCulloch and Walter Pitts. The Pitts McCulloch were some of the earliest scientists who were interested in neurobiology. And they're the ones who came out and said, well, the brain consists of a whole bunch of cells called neurons, and the neurons are all interconnected to each other. And there are firing potentials, and when there is enough stimulation coming in from whatever is connected to that particular neuron, it fires. And they said, well, there are something like 10 billion neurons in the human brain, and that is the architecture of the human brain. So they were very curious about how the brain works, and they came up with that level of a model in terms of a neural network. So that forms the basis for all of this. The second column, statistical physics, I have got below it the portraits of Ludwig Boltzmann and Hosea Willard Gibbs. These are two names you come across quite a bit in deep learning. Boltzmann is more famous for physics. He's the one who came up with ideas of entropy. And today we are invoking him quite a bit. He was also a statistical physics person who was able to talk about energy and probability, and how a gas can be at a certain state and so on, and that high energy states have lower probability, things like these. These are all characterized by Ludwig Boltzmann. We can thank him for that. Hosea Willard Gibbs received his PhD in 1901 in the United States. He was the first person ever to receive a PhD in engineering in any place. So I believe it was Harvard University decided to give him a PhD in engineering. And Gibbs is used quite often. His name comes across at least twice in different topics, important topics in machine learning and deep learning. It comes up when we talk about Gibbs sampling. So when we have a probability distribution modeled by a Markov network, which is a network consisting of nodes and interconnections that is used to represent a probability distribution, we model it by using a Gibbs distribution, which involves multiplying some product of factors determined by the weights of the connections, as well as divided by what's called as a partition function. That was all formulated by Hosea Willard Gibbs. That's the Gibbs formulation. So there is Gibbs sampling and there is a Gibbs distribution, both of which are due to Hosea Gibbs. The last of the photographs underneath is the Turing Award winners for 2019. They are from left to right: Yann LeCun, Jeffrey Hinton, and Joshua Bengio. I've had the pleasure of knowing very well Yann LeCun and Jeffrey Hinton. I had a large project on US postal address reading, and Yann LeCun had just come from France to the United States. He was working at Bell Labs. So we did a joint project about recognizing handwritten digits for the US Postal Service, while I was more involved in the larger architecture of building a complete system for postal address reading. Yann LeCun was more focused on the neural networks, and he invented the idea of convolutional neural networks, which is so widely used today. So he was deserving of this Turing Award that he received last year. Jeffrey Hinton in the middle of that photograph is probably the father of all today's deep learning. He came up with many contributions, one of which was an algorithm called backpropagation, which is when I have a neural network, how do I learn all the weights between the networks? He came up with the idea of a computationally efficient algorithm, which would be used, for example, in supervised learning, where you're applying inputs and getting outputs, and you say, how different is the output than what it should be, and you backpropagate the error, go and modify the weights because you're not getting the right output, and keep doing it forward and backwards, leading to a famous algorithm called backprop. So that was one of his contributions, and he's had many other contributions. One more of which is about what's called as contrastive divergence. When you have a neural network that consists of undirected links between the nodes, how do you learn all the weights? And he came up with a very clever algorithm which is able to learn that for a simple version of a neural network called a restricted Boltzmann machine. It refers back to good old Boltzmann here, a simple machine where we have a bunch of hidden nodes and a bunch of visible nodes. And how do you learn all the weights? He came up with this idea called contrastive divergence algorithm. And Jeffrey Hinton also, whatever he has to say, people all follow all over the world saying this is what Jeffrey Hinton has said about it. So his idea last 2 years ago was about capsule networks. How instead of having simple neurons, you can have a whole set of neurons together, called it a capsule. And so there's been a lot of activity in that area and so on. So he's made contributions throughout deep learning. Joshua Bengio has done some amazing work on things like generative adversarial networks and variational methods and so on, a wide range of contributions. So these are the pillars of those who created today's field of deep learning. So it also gives you a sense of what is involved in learning all about it. There is this biology component, there is the probability and statistics component, and there is all this computing component, which is the distributed computing. So we got all of these components as an essential part of deep learning. Okay, let's move on to the next slide. The next slide gives a simple architecture of deep learning, which says that we understand the world as a hierarchy of concepts. The diagram that's shown below the architecture on the left is exactly that of a convolutional neural network invented by Yann LeCun. It shows how an image is processed in parallel by the slabs correspond to parallel computing there, layers and layers of computing here. and you're reducing the information to higher and higher and higher levels of representation until you perform the final task. It's done in a very simple way. The last task is what's called as a linear discriminant function, and it is able to say, well, that's a dog or a cat and so on. The weights for this network are learned using backpropagation, which is illustrated on the diagram on the right. It's actually a plot of what's called as the loss function, L, of all the weights, W1, W2. These are all the weights that go from one layer to the next layer to the next layer. What are the matrices you multiply the numbers with to get the next layer? And so a loss function is a measure of how the output and the input differ. There are several different loss functions that one could use. And norm penalty loss is a famous one, which is kind of the Euclidean norm of the difference and so on. And so you might be starting at a point on the top of that loss function, which is defined over a space of W1 and W2, which are the different weights here. We are illustrating it for a two-dimensional case, and this could be done in many dimensions. So the loss function might be pretty high in the red region. The goal of the backpropagation algorithm is to keep on changing your weights, W1, W2, until you keep on decreasing the weight, hopefully ending up in the blue region at the bottom, which is, I suppose, the cold region, which is the loss is very little. And this is all done by the equation shown there, WT plus 1 equal to WT. That is the weights at time t plus 1 is what were the weights at WT? And you change that minus epsilon. We call that epsilon as the learning rate. How much are you going to change? How much are you going to learn in one step? And then multiplied by the derivative. The inverted delta symbol there is called nabla, which is a generalization, the idea of dy by dx, the derivative is the derivative of the loss function. So to go from the top, from the red region to the bottom, which is the blue region, you have to keep on proceeding in the direction that's going to improve your situation. You want to keep on reducing the loss. And this tells you how to modify the weight. And you simply compute the gradient at that point and use the gradient to change the weight. This is called as gradient descent algorithm. That equation is a classic gradient descent algorithm. And it is done efficiently by Geoffrey Hinton's backpropagation algorithm, because that computing the gradient can be a very expensive operation. It involves all the parameters. If you're using a million nodes and so on, you might have more than a million parameters. So you can't deal with it in a routine way. So you need a clever algorithm to do this dy by dx calculations efficiently. Okay, let's move on. Okay, so people ask me, can I have a machine learning course? Actually, this happens in my own department. People say, well, can't we introduce a course on machine learning for everybody? Every entering student takes a course in machine learning. And the answer I give is, no, you can't do that. Maybe I'm wrong. For example, here, you can go to any shop, or at least you used to be able to, you pick up networking for dummies, HTML for dummies, or coding for dummies, or database development for dummies, or multimedia for dummies, and beginning programming for dummies, and graphic design for dummies, and even AI for dummies. What about, can we have deep learning for dummies? My answer is, it's going to be not very useful. It involves all these concepts of, the derivatives and even dealing with multidimensional objects like linear algebra and things like that. So maybe it can all be converted into simple library functions, but even then you got to have an appreciation of what's going on to configure it. So anyway, here I'm arguing that machine learning differs from other areas of computer science. So let's see, why is that? Well, I say the calculus plays an important role in machine learning. Calculus is usually a hated subject for computer science people, and they moved away from mathematics because they did not like calculus. But that is a very central piece in deep learning, machine learning, and deep learning. Actually, the physicist, physics and deep learning are very closely connected. The physicist Richard Feynman, who won the Nobel Prize in physics, suggested that the language God talks is calculus. So he says calculus is actually the unifying factor. So what about calculus? If you say, look, what is it I need to know about calculus? Well, first of all, you need to know about derivatives, because we just saw that you need to calculate derivatives to learn. And we need to learn the chain rule of calculus, which says when you have multiple layers, you go from layer to layer to layer, function of a function of a function. So we talk about things like dy by dx is equal to dy by dz times dz by dx. That's called the chain rule of calculus. So it becomes pretty involved when you have composite functions. The chain rule of calculus, you need to follow what that is. So we need to know about maxima and minima. Of course, we know that. Take the first derivative, which should be equal to 0. Take the second derivative, positive or negative, that kind of a thing. We need to know about optimization, which is that's what minimizing the loss function is about. And quite often we come across this thing called Taylor series. It's not like a Taylor series function. It's basically a function which is
Okay, I think again we have problem with the connection from Prof. Srihari. I was so engrossed with the lecture and suddenly the line cut off again. We hope we can get back to him very soon. Our technical team is working on it to get the connection back. Okay, yeah, we're still working on it. Okay, to fill up the time, because I'm not really work with deep learning yet. We just try some projects using deep learning, but not really deep into deep learning yet. So just to fill up the time, okay, if you look at the back of my screen, we have stand at the back. It is a cybersecurity. I'm sitting at the Cybersecurity Malaysia Industrial Lab. This is a collaboration between UTM and also Cybersecurity Malaysia. So basically, this lab sponsored by Cybersecurity Malaysia, and most of the projects that we are doing in this lab is basically on the cyber threat intelligence. Okay, so basically what we do, we apply or we use artificial intelligence, machine learning, and now we are going into deep learning on our project, looking for symptoms or looking for early threats that can later our engine will be able to recognize, for example, like fraudulent activities in the website, or it can be in the forum, because sometimes, especially nowadays during the pandemic era, there are so many cyber threats happen. One of them is the scam. Okay, people are selling fake products, or people are not actually just selling the products, but they say they are selling the products. And once the transaction is done, the buyer sent or paid for the whatever service, or it can be the products. Okay, but they don't give the product back. Or in fact, some scam like Nigerian scams, okay, or love scams, and many types of cybersecurity threats happen. What our lab does is some of the projects that we did is basically to recognize based on the text, okay, whether they have some symptoms of fraudulent activities. Okay, so we have done on recognizing or detecting the fraudulent websites using artificial neural network, and also I think we did on using SVM as well. So basically what I'm trying to say here is that the lab that is sponsored by Cybersecurity Malaysia here, we are working on using AI as a tools in order to combat the security threats. Okay, we are still working on it, on the connection. Our team, yeah, they're still trying. Okay. Okay, maybe just to fill up the time, I'm going to talk more about my lab, because few of us here are the guardian of the lab. basically we work as well on visualization. How can we visualize the trends? For example, we analyze data from normally we get the data from the internet, and then we try to analyze and find the correlation between the intention of the attack and also the critical infrastructure. For example, among the findings that we found is that most of the attacks done or launched towards our government infrastructure, mostly on denial of service and also uh, uh, web defacement. Okay, so finding the correlation, we use some artificial intelligence techniques to find this correlation. So we have the data, but we want to understand the data further. So to do that, we analyze the data and finding this correlation. So normally these kind of projects can be done. In fact, these projects were done by undergraduate students in their final years. So we make it as a project whereby they use artificial intelligence, taking the data related to security and finding the solutions, or in fact finding some information hidden inside the data. So that is what some of the projects that we did. So in terms of visualization, normally we use a software, visualization software, to show this relation. Okay, Prof, you are back.
Yes,
I'm glad you are back. Okay,
yeah,
please
I'm so
continue, Prof.
sorry.
It's okay.
To give you such a bad impression of internet connectivity in India, but it's not really that bad. It's possible to work from home even in India. Just on a Sunday, it's not a good idea to have this, I think, because most of the days it's fine. Okay, so I think I was on the last point. I was talking about calculus. So what all do you need to know about calculus? I think I was on a Taylor series I mentioned. It's an important one because we constantly expand the Taylor series to the first derivative, and then we stop at the second for doing approximations. Ideas of Jacobians and Hessians, which we normally don't encounter in an introductory course on calculus. These are just generalizations of the idea of derivative, because you see so many parallel computations. We need to be doing first derivative matrix, which is Jacobian, and quite often we also do the second derivative matrix, which is partial derivatives pairwise, which is called a Hessian. So this is the kind of calculus that we have to have some familiarity with before you launch into machine learning and deep learning. Okay, let's move on. What about linear algebra? What do you need to know about linear algebra? Well, okay, you need to know about the idea of tensors. So we have a diagram on the left. It says a zero-dimensional tensor is just one value. A one-dimensional tensor is a column of values. A two-dimensional tensor is an array of values, and then a three-dimensional tensor is a cube of values, and then the four-dimensional is an arrangement of the cubes, and then the five-dimensional, six-dimensional arrangement of the cubes, and so on. So tensors are just generalization of scalars, vectors, matrices. It can have many more dimensions. And on the right-hand side, it shows the fibers of a third-order tensor. So we might be referring to the columns of a tensor, the tubes, and so on, or the slices of a tensor, this kind of thing. And why do we get tensors? Just think of an image that your camera captures. It's an RGB image. To get a color image, you have three layers: a red layer, a green layer, and blue layer. Together, when you have those, the eye captures the color of that particular pixel. So there itself, you have a three-dimensional object. And now we might have a video, which is a time-varying three-dimensional object that becomes a four-dimensional tensor. So in all these deep learning modules, deep learning architectures, we have tensors corresponding to even not only RGB, you will also have tensors corresponding to different filter sizes and so on. So you'll simultaneously looking at filters of different sizes of pixels. So these linear algebra concepts become essential. In the bottom, I think I've just shown what a one-dimensional tensor is. It's a vector of numbers, and a two-dimensional tensor is an array of numbers, and so on. So this familiarity with matrices, matrix multiplication is the essential component in. So the idea of transpose of a matrix and multiplication of a matrix and determinant of a matrix, inverse of a matrix, and all these concepts are essential components for an understanding of what's going on in deep learning. Okay, so let's move on. Okay, what about how important is probability in statistics, and what do I need to know about probability in statistics to be a deep learning person? It turns out that is an extremely important component of deep learning. It's not enough if you say, look, I know Bayes' rule, which is, I can do what is probability of, y given x is equal to probability of x given y times probability y divided by probability of x, and that's Bayes' rule. Or its variants called sum rule and product rule of probability. If I know the joint probability of a few variables, how do I calculate the marginal probability of one variable? By summing out the variables you're not interested in, or that would be the sum rule of probability, or the product rule of probability is the joint probability is given by the product of a conditional probability times marginal probability. It is just basic rules. These rules are commonly used throughout again and again and again. Sum rule, probability, and product rule are repeatedly used. Okay, that seems reasonable to learn. But you also have to feel comfortable about probability distributions and value of expected value of a distribution playing a central role. When you say, well, even for a simple task like machine learning for recognizing handwritten digits, you're going to be associating the output with different probabilities that sum to 1, where every different digit would get a probability. Well, you want to know what is the highest value here, or what is the expected value of the output, and so on. So you're going to have to deal with these kinds of things. And not only distributions such as discrete distributions or continuous distributions, but there are things like Gibbs distribution, the same Gibbs I talked about earlier on, where we are defining a probability distribution or a set of nodes interconnected to each other, which means they're influencing variables influencing each other. And so we need to work with a general Gibbs distribution, which is a very common thing to do in machine learning. And then there's a whole subfield of probability statistics, which is more computer science, called probabilistic graphical models, which is about modeling distributions using directed graphs and undirected graphs, and finding out independences in these distributions so that you can compute whatever inferences you want to do efficiently. So you got to have an understanding of probabilistic graphical models. And again, an extremely important topic in machine learning, deep learning, is what's called as Monte Carlo methods. These are methods of sampling. So I have this complicated distribution that is learned by my neural network. So the deep learning neural network has all these nodes and connections, and it has figured out all its weights. So what does it know? It knows a probability distribution. So it has taken all your data and it has learned what is the distribution of all the variables, and then I look at it at different levels of abstraction if necessary. But it has learned a distribution, and then sometimes I want to get a sample from this distribution. Can you give me one sample of the layer that you have here as an example of what an image looks like at that level? This involves going through the probability distribution to get a sample, and that is where the idea of Gibbs distribution comes into play. How do you systematically do that, one variable at a time, knowing the previous variables? There are that's probably the most popular one for deep learning is Gibbs distribution. There are also other things called ancestral sampling and importance sampling and so on. Those come into play, but these are called Monte Carlo methods. And the Gibbs sampling is a particular method called Markov chain Monte Carlo method, or MCMC method. That is again an essential component of knowing. Now, why do you need to sample is the question. One, of course, is to give me a sample of the world that you're looking at. What kind of images occur here? That's how they create celebrity faces. Learn on a lot of celebrities' faces, and you can generate new celebrity faces that don't exist but look so realistic. Or you can generate new text from lots of text it has looked at. But another more practical use of sampling is inference. You're trying to figure out the probability of some event. Even take, for example, inference of, what's the probability if this is a horse? It could very well involve an inference task where you have to calculate or marginalize out the other variables. And that can be an involved task if you have to do it in a standard exact manner. So a Monte Carlo method would be an approximation to that answer. And so anyway, one has to know something about sampling to be in the field of deep learning. And another method is called variational methods. So we are now touching upon the limits of mathematics here. Variational methods come from a specialized area of calculus called variational calculus. In variational calculus, we don't do simply maxima and minima of a function. We are talking about the best possible function. So among all possible functions, or among all possible functions in a family, which function would maximize this quantity? So that's variational calculus. To get a very simple, it's not that complicated. For example, some of you would know the definition of entropy, summation pi log pi. And then we ask the question, what is the distribution for which the entropy is maximum? So what values of pi would give highest value for that particular expression, summation of pi log pi? And some of you would immediately know, I know the answer to that question. It is when all the probabilities are equal, the entropy is maximum. Okay, that's fine, you know the answer. But that particular way of figuring out what was the function, what was the setting for all the parameters that would give you the highest valued function. And so we're talking about the choice of function that would make things maximum. So variational methods rely on that. And so we constantly are asking, which is the function that best fits this model? As soon as you say best, it means you're maximizing a function. So it becomes a variational method. Okay, next slide. Oh, and previous one, there were some pictures in the bottom. The pictures at the bottom are about a GAN and VAE. These are all generative models which use ideas of variational methods. And what you see at the bottom are all kinds of realistic looking photographs. I believe they are of hotel rooms, all beds and things like that. And they simply went around capturing photographs of hotel beds and fed it to a model and then asked it to generate new samples. And those are all very realistic looking bedrooms. It knows exactly how to configure them, what a bed looks like. It has figured all this out and is generating any number of samples that you want, and so on. So this is all examples of samples, Monte Carlo samples that can be useful. Okay, let's move on. All right, and then what about computational complexity? Isn't that simple enough? It turns out that a lot of the problems dealing with probabilistic graphical models, neural networks, they're all really computationally hard problems. The problem of inference in probabilistic graphical model is said to be NP hard. So there is really no solution that can bypass it. You can only get an approximate solution to the problem. And so if it is NP hard, then we have to think of other algorithms. So Monte Carlo methods is one solution, saying, okay, this is too hard. Why does it become too hard? Is even a simple thing such as computing the partition function, which is the denominator of the distribution, involves a summation over all possible variables for over all possible values. So the number of variables in a neural network could be like millions of parameters, millions of weights that are needed, and every one of them, even if they take two values, it is 2 to the power of the number of parameters here. So those are all impossible things to compute. So how are we going to deal with it? And one is, of course, the Markov chain Monte Carlo approach. The other one is the variational approach. So computational complexity is what drives these algorithms. So you got to say, well, okay, I won't be able to compute summation 2 to the power of n when n is equal to 100 or n is equal to 1000. So realization of these things. And below is one more example confronting the partition function. And that's where we get Monte Carlo method. So we constantly need to compute the derivative, even to compute backprop and so on. And so you're going to have to deal with it. So the constant companion is computational complexity, and says, okay, we have an algorithm, but we can't use the algorithm. So let us come up with another algorithm, and so on. This is the kind of chain that leads us from one algorithm to a different algorithm, because we are at the edge of computing here. Okay, let's move on. So, so those are the main components, the four main components we talked about was calculus, linear algebra, probability theory, and computational complexity. So, how do we deal with it? Do we have to write code to do, derivatives and so on? Fortunately not. There are all these deep learning frameworks. This is a picture from about 2-3 years ago, 2017. All the various libraries, Python libraries that were available, such as Keras and TensorFlow and PyTorch and so on. There are some older ones that had already been discontinued, like Cafe and so on. But not all of these are in existence today. Some seem to be dominating. So many of these deep learning frameworks will give you, okay, backprop you don't have to do. It can be done by a library function call. But architecting it, how many layers you're going to need, what do you need that for, and all the variants of the optimization algorithm. There are so many optimization algorithms to figuring out the best possible weights to minimize the loss function and so on. All of that requires a knowledge of what is going on under the hood for each of these library functions. Okay, so there are all these frameworks. Let's continue. So then we can talk about how deep learning disrupts computer science, and in a sense, it is changing everything. The software developer at the present time writes and maintains layers of tangled code. We write logic, and that's what even the knowledge-based AI was about. We're talking about the present and the future. At the present time, we are just feeding the data to these machine learning programs. So, what is the work of a software developer? It might be more about that you are a teacher in supervised learning problems, which is about you are giving an input output examples as opposed to just learning a distribution. So, the job of a software developer is to write code to execute these algorithms.
Okay, as much as we don't want this to be disconnected, but it happened again. I'm really sorry on behalf of everyone, the team here, because we didn't expect this connection to be frequently disrupted. Okay, but it seems like we have another few more slides. I think about 3 or 4 more slides to end the presentation. To our viewers, I would like to remind, if, for example, you have any questions, you can just type in the comment at the Facebook. Okay, just type in the comment. Our team will read your question, or in fact, me, I'm going to read the question, and we're going to post the question to Prof. Srihari so that he can answer. Okay, because of the time limit, if there's going to be a lot of questions to be asked, maybe we don't have time to finish to read every questions. We're going to pick the questions, but if the questions is quite the number of questions is not that many, maybe we would be able to answer all of your we would be able to post all the questions that you post at the comment. There was one question. How was your attachment with Prof. Srihari Lab? You may want to share your experience. In fact, I got to know him last year personally from his publication. I read his publication previously because my domain is more on security and his domain on the machine learning and artificial intelligence. Somehow it comes to one point where it intersects. Okay, because most of the solutions that we use, we do deploy artificial intelligence. So in fact, we are embarking, our team is trying to embark, or in fact, at the stage of embarking the collaboration with Prof. Srihari. Most of the time, we collaborate with another professor, quite a prominent professor as well, Professor Ajith Abraham, who will be one of the speakers. We expect him to give a talk sometime in this month as well. The collaboration that we have in terms of research, okay, because he is quite well known in the machine learning and at the forefront. Okay, so when we have a problem, sometimes we have like a solution that we propose to him for him to judge or for him to give some opinions. Okay, so in that case, sometimes he give a feedback which is quite positive feedback, and we fix our solution. And in terms of publication, we do write our papers together. In this case, with Prof. Ajith Abraham, not yet with Prof. Srihari, because we just got to know each other personally about a year ago. But most of the time, as I said before, our collaboration is more with Prof. Ajith Abraham. As again, he will be invited as well. In fact, we have invited him. He's going to give us the date, appropriate, suitable date for him to give a talk in this webinar series. Okay, so back to the kind of collaboration that we normally have with the professors from outside UTM. Okay, I think we are getting him back. Okay, Prof, please continue. Thank you. Please continue.
Your audience may be actually be enjoying having you speak to them in the
No.
middle. I think great idea. Listening to one person can get monotonous for anybody, and getting another perspective simultaneously is a great idea. This is called distributed lecturing. Right, so we operate simultaneously. So anyway, good. I don't think we are losing too much in the whole process. All right, so I was just mentioning disrupting. I'm almost finishing up so that we can deal with the questions. So as a software developer, future is about curating data. Mathematics, what kind of mathematics computer science people should know? Well, the classic approach for computer science has been you need logic, you need discrete mathematics. Now we are saying probability theory is important, calculus is important, linear algebra. That's also about continuous mathematics. So continuous mathematics is important for deep learning. And then what about programming environments? We've been saying C++, Java, and so on. But it seems like the direction is Python and TensorFlow, PyTorch, Gluon. And some people are arguing in 10 years, most software jobs won't involve programming at all. But anyway, that might be a little bit of a stretch to say. It's all about data curation and very little of programming. And the hardware, mostly CPUs have been the way. And of course, we're already transitioning into GPUs, which is all about distributed computing. All right, so this is how all of this disruption is taking place. And actually, some of the ideas that I have on this slide comes from the director of AI at Tesla. And his name is Karpathy, Andrew Karpathy. He is the lead of AI at Tesla. And he was saying in his laboratory, he's got two types of code that goes into all this automation, automated driving, and so on. He says one type of code is written by human beings. He refers to it as software 1.0. Uses a classical stack. Its code is written in Linux, Apache, MySQL, Python, Perl, like that. So that is the classic type of code. And then he's got all this code in his lab that is all done by machine learning programs that follow you as you drive the car around. It has looked at all the images, it has figured out what exactly to do. It was not written by anybody. And it is all in a user-unfriendly language. And there are millions of weights in this type of code. And there is no human involved in its coding. So there is one type which is all about software 1.0, and another type is software 2.0. And the argument has been made by other people. Yeah, they're saying more of this, and they argue that a lot of the software 1.0 could be replaced by software 2.0. And there are, I think my next slide says what are the advantages of 2.0 or 1.0. Let's look at the next one. Oh, okay. No, I don't have a next slide. I'll just mention it. The advantage of software 2.0 is that it is, the debugging and all that is not up to human beings to look through them. And it's it is all fairly straightforward. It's all one level to the next level. Humans can't really understand it, but not even worry about debugging. It's the data sets and parameters and so on. So that's that. And then such code can be easily put into silicon, converted into hardware. And usually, this software 2.0 is going to be smarter than software 1.0. because the neural network programs turn out to figuring out variants that a human being didn't really think about. Okay, let's go on to the last slide. Maybe that sounds like the conclusion. Okay, the next slide, please. Oh. Okay. All right, we are back there, right? So, all right, let me just conclude with this slide. So, what are the points I'm making here? So, deep learning is inspired by neurobiology, statistical physics, and distributed computing. Deep learning methods heavily borrow from traditional science and continuous mathematics. So, knowing some physics and knowing some continuous mathematics, I think, is a useful thing if you're going to be a researcher particularly. Deep learning involves calculus, linear algebra, probability statistics, computation complexity, distributed architectures, and that deep learning will disrupt computer science itself and software development. Okay, so having said that, I'm happy to take on any questions. Hopefully, the internet will be okay.
Yeah.
Anazida, you want to
Yeah. Okay.
join
Yeah.
the
I would
discussion?
like to open. Yeah. Okay. Thank you, Prof. Hari. On behalf of UTM and our viewers, I would like to express our deep appreciation for your inspiring presentation. I believe your interesting talk may have shed some light and spark an interest for many of us to learn more on deep learning. Let us now take a few questions from our viewers. Okay. 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 We have. Okay. The first question is from Dr. Murad A. Rassam. Okay, actually he was our PhD student, now serving in Saudi Arabia as an associate professor there. Okay, the question is potentials of applying deep learning to cybersecurity issues. Is there any potentials, or maybe you can give some examples of how we can apply deep learning in cybersecurity issues?
Okay, first of all, deep learning looks like it can be used in any domain, any field that you need to solve problems in. It looks like deep learning can help. AI can help, and I talked about how deep learning is a good approach to AI. So if you have a need for writing code for some task, deep learning can help. Now, coming specifically to cyber security, it's not an application that I've had a lot of familiarity with, but I know one example I believe is anomaly detection. That you have normal events that happen, and you would like to figure out whether a particular sequence of events is anomalous. That is not a normal user that is encountered here, the sequence of operations and so on. And so one can have a machine learning program learn what is normal and what is abnormal, and says, okay, so it is not part of this. So there is only one distribution here, which is that of normal distribution. I guess in the sense normal in a different way. So we have a distribution of the normal behavior, and here is a abnormal behavior, and to be able to see whether it belongs to that distribution or not. So that becomes a one class problem. It is not a two class problem, saying does it belong to that distribution or not. Does it belong to the tail of a distribution that's so far out on this distribution, and say that is how we detect that this is a security issue. So I'm giving you the answer in a very broad way, but I'm sure there are many specific ones. Cybersecurity can also involve authentication and so on. I guess even biometrics and things like that may be connected to cybersecurity. If that's the case, then you have a tremendous amount of application there in terms of images, and faces, and fingerprints, and voice, and all these things. Can all have a role in cybersecurity. So, anyway, I look more at the methods rather than the application. So, I think you all can be more clever about figuring out, my problem, I can formulate it. You can formulate it in a couple of different ways. It doesn't have to be a supervised learning problem. You can also have unsupervised learning. Is it learning a distribution? Maybe that's the normal way of behavior is a distribution. So you're learning a generative model, which is a probability distribution of what's happening with all the data that you have, and figuring out new data where it fits in with this distribution. So you can use both supervised learning and unsupervised learning for that problem.
Okay, the next question. Yeah, we have from Yasir Zahidi. The question is, what is the best techniques that can be suggested for wireless channel modeling? For example, the one getting the best fit models based on the experimental measurement data.
Oh, wow. So that is a detailed
Best fit
question
model.
about communications here, communications engineering.
Yeah, wireless channel modeling. Mhm.
Wireless channel modeling. So, you know, I got my bachelor's degree here in India in communication engineering, but a very long time ago. I became a
Okay.
computer scientist after that. So I'm sure there are, basic questions here about, separating signal from noise. You know, that's one of the classic problems that use probability and entropy and these kinds of ideas. So those are all those will definitely take advantage of learning distributions when you're talking about experimental data. When you're basically modeling probability distribution, think of machine learning as a way to understand the probability distribution. So when you have data, you have probability distribution. So you can model the distribution, and in a very intelligent and a clever way, that it is not just at the signal level, low level. It actually can be used to learn at a very high level. So you can use probability distribution to learn probability distribution.
Okay, I think we lost him again. Yeah, I think we lost him again during this question and answer section. So basically, I think what I can conclude from his answer to the question posed by Yasir Zahidi is that as long as you have the measurement data or the data, the machine learning can be used to understand the data and model and come up with a model based on the training data that is being exposed or being shown to the machine learning. So the answer is yes. I think in this case, machine learning, I think the answer from Prof. Srihari, what he was trying to say is that yes, machine learning can help in understanding the data that needs to be trained. That means we will come up with a model based on the measurement data that is being exposed to that machine learning. Okay, we are waiting for him to come back. Perhaps what the team can do, you can display the question now. Can you display the question? The next question? Okay, this is quite, I think, very interesting question. What is next after deep learning? Are we going to have deep learning? Because we know that after deep learning is a function of a function of a function of a function. It has so many layers. Okay, if you are familiar with neural network, we have like a simple 2 layers or 3 layers, or in fact just 1 layer. But deep learning, you can imagine having multiple layers. It can be 10, it can be 15 layers. So all these layers is a function. So the output from one function will be fed to the next function, to the second layer, and so on. So we are going to wait for Prof. Srihari to answer this question, because I myself do not know what will come after deep learning. This is quite a futuristic question, I suppose. Okay, we are still trying to get to. Okay, now as what Prof. Srihari said, I may have to give lecture as well. I'll try my best to answer within, if the question is posed to me, I'll try my best to answer. Okay, this is a question from Dr. Murad Rassam again. What are the potentials of applying deep learning in security issues? Okay, currently, I'm just telling you what we are doing. Currently, we are working on few. Okay, I think we got him back. Okay, Prof. Srihari, back to you.
Yeah, I feel like I'm some kind of genie coming in and out of the room. All right. So the previous the question was about how can we be used in wireless communication. That's
Yes.
exactly what we are doing here, and we are repeatedly failing. Okay, so.
Okay, but it's okay. I think you already answered that question. We can move to the next one from Muhammad Amir. Prof, are you with us? I think again we lost him. Okay, Muhammad Amir, we have to hold you have to hold the question first, okay? Because this question should be answered by Prof Srihari. Okay, can the team go back to the question posed by Dr. Murad just now? Okay, so what we are currently doing, we use deep learning. We work on the South China Sea conflicts. Okay, basically we want to know what are the strategies, because South China Sea conflicts is basically quite interesting issue, because Malaysia is one of the entities in South China Sea, and whatever happened in the region may affect us. Okay, so what we do now is we are trying to understand the strategy of these countries, especially the China, the Vietnam, Philippines. Okay, if there is any crisis, what would be? It's more like predictive. What would be the reaction from the countries? For example, we know that in the area of South China Sea, we have a problem whereby China tried to get some territory close to Philippines and Vietnam's, and they reclaim the area. For example, they built an artificial land or artificial island, okay, and they put their army there. Okay, so these kind of things have sparked some discomfort with the neighboring countries. For example, this happened to Philippines and China. So what happened is that one of the incident, the China lost to the Philippines, because they are quarrel, not really, they are like claiming the land. This is, China said this is my area, and another country, which is Philippines, was saying that this is my area, and so on. So this particular issue was brought to the Hague, which is the International Court at The Hague. Okay, so when the verdict was out, okay, it seems like it favors Philippines. And right after the verdict was out, okay, there was like cyber attacks happened to Philippines government, whereby most of the government platforms were hacked, and they stripped the security layer, whereby the information in the government platforms of Philippines get exposed. Anybody can get access to this sensitive information. So this is one of the impacts of the conflicts. Okay, because nowadays we see that for someone to go and invade somebody else's country is quite very explicit, right? People can see, but you can launch an attack. For example, you can launch cyber attacks to that particular government. So in the case of Philippines, not only the government platform being hacked, all the websites were defaced. I'm not sure but majority of the government websites were defaced, and then they sent viruses as well. Here we know that virus is also a term that we call in cybersecurity domain. Okay, so they send the virus to this government of Philippines. So you can see that the impact is very big. So we use deep learning to understand the crisis happen in the South China Sea. Okay, so this is one of them. And we also use deep learning in, I think another study that we did was in the fraudulent website detection as well. In fact, I believe that in intrusion detection, we can use deep learning as well, because we need to learn. Okay. Now, Prof. Srihari is back. Prof. Is Prof. Srihari there? Okay, now the screen is off again. I'm sorry. Okay, what we are trying to do here, we are doing intrusion detection as well for the cloud computing. We are using deep learning as an engine to detect the malicious traffic that comes to the network. So this is what we have been doing so far with deep learning. Okay, maybe next question. Okay, we reserve this question to Prof. Srihari because he is our prominent lecture today. He's giving the lecture today. So the next question comes from Buambale Rashid Ramadan. Deep learning is mostly meant for computer vision things like image processing and etc. How can we tap into this for other applications? For example, second question. AI has come in as a challenge for security experts, threatening the security field in various aspects. The solution could be quantum cryptography, but it is taking long to be achieved, to be active. Where do you see the world of security in this era of AI and deep learning? Okay. Okay. The team, what the team is trying to say here, the team is trying to get the connection back to with Prof. Srihari. But if we cannot get within 5 minutes, we have to end the session. I'm really sorry for the interruption because we didn't expect the connection is quite bad today. Okay. The question to Buambale Rashid Ramadan, I'm going to answer a little bit on the cybersecurity part because this is what my bread and butter, this is what we are doing in this lab. The way I see it, AI and deep learning is more towards helping us because we know in the era of big data, the data is so huge and it comes from various sources, different formats and so on. Okay, so to understand the information or the knowledge within these voluminous data, we need some technique like AI or deep learning. Okay, so I see deep learning and AI come to the rescue for us to help us combating with the attacks or combating with the threats. Because, for example, one interesting attack is called APT or the advanced persistent threat. Okay, this APT or advanced persistent threat is not like other threats that we have seen in the past. Okay, their behavior is quite different. Okay, because they want to camouflage themselves as if they are the real program or the original or something which is good program, not the malicious program. So this APT changed its strategy because they're going to fool us as maybe a security analyst or security engineer and so on. They change their behavior because of they want to fool us. So we no longer in security, we cannot depends on rule based. If you can imagine, you have antivirus. Okay, what antivirus has is actually a list of signatures. Okay, signatures of the known viruses. Okay, so you can imagine the hassle of updating as the new virus comes. You have to get the signature and you have to put in the list itself. So the list will continue growing. Okay, so that is called what we term it as rule based, or because it depends on the rule or it depends on the signature list. Okay, so and you can imagine the hassle because somebody has to update, you have to wait. That's why if you look at it, if you notice, you have to upgrade your antivirus from time to time so that the new viruses, definition of new viruses and also signatures can be updated in the list. Okay, so now let us imagine now when Prof. Srihari was talking about anomaly detection, meaning we learn what is normal. Okay, we learn what is normal. So anything which do not conform with normal can be considered as abnormal. Okay, Prof. Srihari, welcome back. Okay, we really need you here.
Okay. Well, we learned that we got to be careful not to do this on Sundays. That's all. Okay, so
Exactly.
go ahead.
have to, yeah. So can you display, Tim? Can you display the question again so that I can read to Prof? Okay, I cannot answer this, Prof. Okay, because he was asking quite a futuristic question. What is next
Yeah.
after deep learning from your point of view?
Well, you can answer this question as what is next in deep learning as opposed to what is next after deep learning, right? So what's coming up is what are the research topics that are of upcoming importance. And we have largely focused on supervised learning and unsupervised learning so far. And there is also a couple of other variants of it. One is called semi-supervised learning. The other one is self-supervised learning. And semi-supervised is interesting enough. It says, look, we cannot sit and label lots of data, but we can label some of it, and then can you figure out? So it's a combination of supervised learning and unsupervised learning, and we can learn a lot by combination. Self-supervised learning is even taking it a little step further, where in small amounts of data, it's figuring out what could possibly be the labels, and even less is said about it. So I think Jan LeCun feels that this self-supervised learning is an extremely important area. The other areas are, I feel, representation learning is still in the early stages, so that you can have explainable, right? Explainable AI. So one of the complaints about deep learning is that it just gives you all these layers and layers of numbers, and that is no good if you want to have a rational explanation of why are you saying it is this disease, or why are you saying this is what we should do. It is not explainable. And so how do we incorporate explainability? Well, that is again a debatable topic, because people say, look, you can either make it perform as well as possible, or we can make it perform less well, where your focus is on explanation. So I feel explanation based learning is a possible area, but I would not wholeheartedly endorse it, because it takes away from the mainstream of deep learning. We still have to do a lot more in the mainstream of deep learning before we say, okay, let us stop and let's focus now on is the learning explainable. So maybe explainability and the type of supervision. Jeffrey Hinton, if you ask him, because everybody has an opinion on what's the next important thing, Jeffrey Hinton will say capsule networks. What we are capturing at these nodes may not be enough. You need to carry along more information as you go from layer to layer. That seems like a somewhat of an incremental answer to the question, saying it's going to be instead of units, you're going to have capsules. So that is one possibility. So these are three or four. Maybe there are a few more you can think about, but there aren't that many other avenues I can think of. Self-supervised learning or natural language processing is driving a lot of deep
Yes.
learning, and there they have come up with very interesting models. Where they have moved away from standard recurrent neural networks based on LRU and LSTM and so on. Now they have come up with new things called transformer architectures, which kind of do away with the recurrence, and some new models there. They seem to be very revolutionary in terms of the kinds of text that they can generate. And actually, one of those companies, OpenAI, I believe, would not even release their software because it is too powerful that it can generate any amount of text you want on any topic. You just give it a little bit of a start, and it will write a lot of realistic sounding things about it. The not only the sentences are meaningful, the paragraphs are meaningful, and the whole passage is meaningful, and so on. So the creativity is something. Maybe creativity is the area. You can say, well, is that the next thing? Is to have programs that are very creative in terms of writing and composition, but that's already there. Deep learning is already doing it. We are able to generate beautiful paintings, and we can generate new bedrooms or new churches, or whatever you want to design, or create new people who are very realistic looking. These are all there already. So within deep learning, it's not like it's outside of deep learning. So deep learning itself has much to go, and so we can say deep learning is here to stay with all these new variants that are coming up.
Okay, Prof. I think because the time is already 5:34 here, I think that would be our last question. Okay, so thank you for the interesting talk on deep learning and for entertaining questions from our viewers. We all really enjoy your presentation, though we have hiccups, but we really enjoy your presentation. We appreciate you making time in your busy schedule to deliver this lecture. Thank you again, Prof. Hari, and we hope we can continue to collaborate in the future. To our
Yes.
viewers, to
Yeah.
our viewers, we are sorry for the hiccups happened at the beginning of the lecture. We will email your question to Prof. Hari and get back to you. And last note, I would like to remind everyone that we have many more interesting lectures to be delivered by many prominent professors from all over the world. Stay tuned. Please like, share, and comment the Facebook page of Faculty of Engineering, Universiti Teknologi Malaysia. Now, I would pass back over to Prof. Rafiq. Stay tuned, stay safe, and thank you.
Right. Thank you so much, Anazida. You've done a great job actually as as an assistant to Prof. Hari today. And to Prof. Srihari, our deepest gratitude to you for sharing your knowledge with all of us. Thank you so much. And to all of you watching this program throughout the globe, of course, we are sorry for the disruption, but do hang out with us. We have more sharing session from professors throughout the globe. And thank you for watching. I'll see all of you in our next episode of UTM Engineering Distinguished Lecture Series. Bye for now.
Thank you very much. Enjoyed it.
Thank you, bro.
Yeah.